Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's chapter is Gravitation, one of the most formula-dense derivation-heavy chapters in JEE mechanics and one that rewards genuinely understanding the physics rather than just memorizing results. In this video we'll cover Newton's law of gravitation, gravitational field and potential, Kepler's laws variation of G, escape and orbital velocity with full derivations, gravitational potential energy, satellites, and the specific problem-solving traps JEE loves to set here. Let's begin. Newton's law of gravitation states that every point mass attracts every other point mass, with a force directed along the line joining them, with magnitude equal to G times m1 times m2 divided by r squared, where G is the universal gravitational constant 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, an extraordinarily small number. That's exactly why gravity is by far the weakest of the four fundamental forces, and why you don't feel yourself gravitationally attracted to nearby objects in daily life. This is an inverse square law. Force falls off with the square of separation, and it's a central force always acting along the line joining the two masses, which has an important consequence. Since talk about either mass is zero, angular momentum about that point is always conserved, a fact JEE uses repeatedly in orbital mechanics problems. For a system of multiple masses, the net gravitational force on any one mass is found by vector superposition. Calculate the force due to each other mass individually, treating each pair in isolation, then add all these force vectors together. This superposition principle is what lets you handle problems with three or more interacting masses or continuous mass distributions by breaking them into pairwise interactions. Integrating a critical JEE trick for a uniform spherical shell, the net gravitational force on a point mass placed anywhere strictly inside the shell is exactly zero, while outside the shell, the entire shell behaves exactly as if all its mass were concentrated at the center. This shell theorem, proved rigorously using Gauss's law for gravity, is the single most tested conceptual result in this section. The gravitational field at a point is defined as the gravitational force experienced per unit mass placed at that point. It's a vector quantity with the same units as acceleration, and for a point mass m, the field at distance r has magnitude gm over r squared, directed toward the mass. Gravitational potential, in contrast, is a scalar quantity, defined as the work done per unit mass in bringing a test mass from infinity to that point. For a point mass, this works out to be negative g m over r, and the negative sign is genuinely important and frequently tested. It reflects the fact that gravity is always attractive, so you must do negative work, meaning the field does positive work. To bring a mass in from infinity, potential is taken as zero at infinity by convention, and becomes increasingly negative as you approach the mass. The relationship between field and potential is that the field equals the negative gradient of potential in one dimension, E equals minus dV by dr, meaning the field points in the direction of decreasing potential, and physically, the field is strongest where potential changes most rapidly with distance. For a uniform solid sphere, the potential at any external point again behaves exactly like a point mass at the center, but inside a uniform solid sphere the potential varies continuously and smoothly, following a different quadratic in our formula, distinct from the point mass formula that applies outside. This inside versus outside distinction for solid spheres, as opposed to hollow shells, is a classic source of JEE trick questions. Kepler's three laws derived empirically from observational data before Newton later proved them mathematically from the inverse square law itself. Display planetary motion with remarkable precision. Kepler's first law, the law of orbits, states that every planet moves in an elliptical orbit with the Sun located at one of the two foci of that ellipse, not at the center. This is genuinely important. Planetary distance from the Sun continuously varies throughout the orbit. Kepler's second law, the law of areas, states that the line joining a planet to the Sun sweeps out equal areas in equal intervals of time, and this is directly mathematically equivalent to conservation of angular momentum. Since gravity is a central force producing zero torque about the Sun, angular momentum must be conserved, which is exactly why a planet moves fastest at perihelion, its closest approach to the Sun, and slowest at aphelion, its farthest point. This connects directly back to the central force property discussed earlier. Kepler's third law, the law of periods, states that the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. T squared is proportional to a cube, and this specific relationship can actually be derived directly from Newton's law of gravitation combined with the requirement for circular orbital motion by equating gravitational force to the required centripetal force, giving JEE a favorite technique, deriving T squared proportional to r cubed from first principles for a circular orbit rather than simply quoting it. The acceleration due to gravity g equals gm over r squared at Earth's surface, but it's genuinely not constant everywhere, and JEE tests all three major variations in detail. With height h above Earth's surface, for h much smaller than Earth's radius r, g at that height approximately equals surface g times the quantity 1 minus 2 hours over r. So g decreases approximately linearly with height for small heights. This is a first-order binomial approximation genuinely worth memorizing and being able to rederive quickly under exam time pressure. With depth d below the surface, g at that depth equals surface g times the quantity 1 minus d over r. Notice this decreases linearly all the way to exactly 0 at Earth's center, unlike the height case. And this particular result follows directly from the shell theorem. Only the mass enclosed within radius r minus d actually contributes to the gravitational pull at that depth. The mass in the shell above you contributes precisely 0 by the shell theorem covered earlier. With latitude, g also varies due to Earth's rotation. Effective g equals true g minus omega squared r cos squared phi, where phi is latitude and omega is Earth's angular velocity. This means measured g is smallest at the equator, where the centrifugal effect is maximum and directly opposes gravity, and largest at the poles, where the rotation axis passes directly through the point, and centrifugal effect is zero. Escape velocity is the minimum speed an object needs at a planet's surface to escape that planet's gravitational pull, entirely reaching infinity, with exactly zero residual kinetic energy. And it's derived directly from energy conservation. At the surface, total mechanical energy equals kinetic energy, 1/2 mv squared, plus gravitational potential energy, minus gmm over r, and at infinity, for the minimum, just barely escaping case, both kinetic energy and potential energy are exactly zero. Setting initial total energy equal to final total energy, 1/2 mv escape squared minus gmm over r equals 0, and solving directly for v escape gives the square root of 2 gm over r, which can also be rewritten using g equals gm over r squared as the square root of 2 grams r, a form that's often more directly useful for quick numerical calculation in JEE problems. For Earth, this evaluates to approximately 11.2 kilometers per second, a genuinely useful benchmark number worth memorizing directly. A critically important, frequently tested point-shape velocity is completely independent of the escaping object's own mass, a feather and a rock, launched from the identical location. Both require exactly the same escape velocity. This is a direct, elegant consequence of gravitational mass and an inert IL mass being exactly equivalent, which is precisely why the object's mass cancels out completely and identically from both sides of that governing energy equation. Orbital velocity is the specific speed needed to maintain a stable circular orbit at a given radius, found by equating gravitational force to the required centripetal force gmm over r squared equals mv squared over r. Solving for v gives the square root of gm over r. Notice this decreases as orbital radius increases. Satellites in higher orbits genuinely move slower, not faster. Comparing this directly to escape velocity, v escape equals the square root of 2 times v orbital. Escape velocity is always exactly root 2 times the corresponding orbital velocity at that identical radius. A clean, elegant, frequently tested relationship worth memorizing directly as a ready shortcut. Gravitational potential energy of a two-mass system is defined as minus gmm over r, taking the zero reference at infinite separation, and total mechanical energy of a satellite in a stable circular orbit works out to exactly minus GeM over 2r. Notice this total energy is negative, which correctly physically indicates the satellite is in a genuinely bound orbit, unable to escape on its own without an additional energy input. The magnitude of this negative total orbital energy is called the binding energy of the satellite, precisely the minimum additional energy that must be externally supplied to that satellite to send it completely to infinity. And it conveniently, elegantly equals exactly half the magnitude of the satellite's own gravitational potential energy at that same orbital radius. A geostationary satellite is one that appears completely stationary relative to a fixed point on Earth's rotating surface, which requires its orbital period to exactly match Earth's own rotational period, 24 hours, and it must specifically orbit directly above the equator, in the same rotational direction Earth itself spins. Using Kepler's third law, t squared proportional to r cubed, with t fixed at 24 hours, the required orbital radius works out to a specific, fixed value, approximately 42,000 kilometers from Earth's center, meaning roughly 36,000 kilometers above the actual surface. This fixed altitude is exactly why all geostationary communication satellites cluster at that same specific orbital radius. Weightlessness experienced by astronauts in an orbiting spacecraft is a frequently misunderstood concept. It's absolutely not because gravity is somehow absent or negligible up there. Gravity at typical low Earth orbit altitudes is still nearly as strong as at the surface. Weightlessness instead occurs because both the astronaut and their entire spacecraft are continuously, simultaneously in free fall together, falling toward Earth at the exact same acceleration, so there's genuinely no relative normal contact force between the astronaut's body and the spacecraft's floor, which is precisely what a bathroom scale would otherwise measure as apparent weight. This same freefall principle is exactly why objects released inside an orbiting spacecraft simply float motionless relative to the cabin rather than actually falling to the floor. A few specific traps show up year after year in JEE gravitation problems, and knowing them in advance saves genuinely valuable exam time. The first trap: students frequently confuse the height variation and depth variation formulas for G. Remember, height decreases G roughly linearly only as an approximation for small h, while depth decreases G exactly linearly all the way to zero. If a problem gives you a height or depth comparable to Earth's own radius, you cannot safely use the small h approximation. You must instead go back to the full, exact inverse square formula. The second trap involves energy conservation problems combining both gravitational potential energy and kinetic energy. Always be careful to correctly write potential energy as negative GeM over r. Sign error here is easily the single most common mistake in these problems, and it silently flips your final, numerical answers sign, completely changing whether an object escapes or remains bound. The third trap concerns changing orbits. When a satellite moves from one circular orbit to a larger one, its speed actually decreases, but the energy required to reach that new higher orbit still increases overall. Since total orbital energy becomes less negative as radius grows, students often incorrectly assume higher orbit automatically means higher speed. Exactly the opposite is true. Finally, for problems combining Kepler's third law with orbital mechanics, always double-check whether the problem is asking about the semi-major axis of an elliptical orbit or the fixed radius of a circular orbit. These formulas are related but genuinely not interchangeable without care, and JEE examiners deliberately exploit this specific ambiguity to test real conceptual understanding rather than simple formula memorization. Let's recap this entire chapter. Newton's law of gravitation, F equals Gm1m2 over r squared, is a central inverse square force, and the shell theorem tells us force is zero inside a uniform shell but acts like a point mass outside. Gravitational potential minus Gm over r is always negative, and Kepler's three laws describe elliptical orbits, equalaria sweeping from conserved angular momentum, at t squared proportional to r cubed. G varies with height, decreasing roughly linearly, with depth decreasing linearly to zero at the center, and with latitude, due to Earth's rotation. Escape velocity root of 2 gm over r is independent of mass and equals root 2 times orbital velocity at the same radius, while total orbital energy negative gmm over 2r. Thus a satellite is bound with binding energy equal to its magnitude. And geostationary satellites orbit at a fixed radius with a 24-hour period above the equator, while weightlessness in orbit is simply continuous free fall, not the absence of gravity. That's the complete gravitation chapter for JEE. Keep the shell theorem, the escape versus orbital velocity ratio, and the G variation formulas sharp. They show up constantly in numericals. If this video helped, please like it and subscribe to Padhai Karlo for more JEE preparation content just like this. See you in the next one.